Okay, good evening, everybody. Welcome to our February-March meeting. We almost had two weather cancellations, but I think we dodged this one. Thank you for coming out. But just as an announcement, our new member, Eric Kujala here, he is my buddy. We've explored a lot of meteorite craters, and he's offered to use his HD video cameras to tape all our meetings. So this is actually very, very good for this one because of the fact that a lot of people won't be here for the weather. So we will have the DVD of each meeting in the library, and we can sign it out. There's going to be a lot of presentations we've had in the past that unfortunately, you know, they were great, but they're gone. But now we're going to have them on DVD, and they'll be here forever. Thank you. And this is Eric Kujala here, my cohort and
Canoe buddy.
Canoe buddy, yes. Yeah, we did how many kilometers this summer? Over 100 anyway, on this canoe. Anyway, welcome. And at this point, I will let Chris do something.
Signal is dying.
Too much serious along. Now the lasers are arcing. The guide cameras fried. I'm a victim of a disc crash. My career has just died. Last thing I remember, I was running for the door. I had to find the passage back to the lab I had before. Relax and the key out.
It'll just take one more tweak.
Close the dome anytime you like. You can never leave.
Just one of those things that don't really know what to expect when I stand up here.
Courtesy of YouTube.
Thank you very much, Chris. Okay. At this point, I'd like to introduce Paul Harrison, our Vice President, and he's going to let us know about all what's happening with Messenger. Paul?
Does this one have a laser pointer on it? No, it doesn't. Okay, so as I'm sure many of you know, Mercury Messenger is a spacecraft that had just completed its first flyby of the innermost planet of our solar system, and that was back in January. So had put this together for the February talk, and of course the February talk is now the March talk, but they're still getting some very interesting data back from the images that were taken, so it's still very topical. So if we go to the first slide. So why are we visiting Mercury? Maybe go to the, I'll just go. Well, very little is known about the planet Mercury. And the reason very little is known is largely, whoops, it's not advancing here. There we go. It's very difficult to observe from the Earth. And this picture you see in the background is it's a composite of several images taken of Mercury. And I'm not sure if that's the sunrise sky or the sunset sky, but again, because Mercury orbits very close to the sun, we never see it very far from the sun. We can only observe it just before sunrise and just after sunset. So up until the era of spacecraft, we really knew very little about it. In fact, only one spacecraft before Mercury Messenger had ever visited the planet, and that was Mariner 10, and that was back in 1973 through 75. Made several flybys of the planet. And again, it did not orbit the planet, so more than 50% of Mercury's surface was never mapped by Mariner. So, and that was over 30 years ago. So just a few little facts about Mercury. The orbit period, the length of time it takes Mercury to orbit the sun, is 89 Earth days, so about 3 months. Its sidereal rotation period, which means the rotation period with respect to the stars, is 59 Earth days, or 2 months. So in other words, if you were standing on the surface of Mercury and there was a certain star that was directly overhead, 59 days later it would be right overhead again. And so again, we have an orbit period of 3 months and a rotation period of 2 months. And that ratio is not accidental. It's something called resonance. Basically, Mercury orbits 3 times and rotates in that same period twice. And in fact, for much of the early period of astronomy, astronomers believed that Mercury was actually tidally locked to the sun, in the way that the moon is tidally locked to the Earth. One face always staring at the sun, one face always staring away. But in fact, Mercury does rotate with respect to the sun, but because it's so close to the sun, the tidal effects are big enough that it spins very slowly in relation to its orbit, and it spins in a 2-3 resonance with its orbit. Now, what that means in terms of the Mercury's day in the sense of a solar day is that if you're standing on the surface and the sun is directly overhead, it is actually 6 months before the sun is back overhead at that same spot. Now, being very close to the sun, of course, on the daytime side, it gets quite hot. In fact, daytime temperature goes up to about 430 degrees Celsius. But on the positive side, it's a dry heat. Now, on the nighttime side, however, it actually gets extremely cold. And that's because Mercury has little to no atmosphere, certainly nothing substantial enough to trap heat. So on the night side, you're looking at temperatures that are down to about 180 degrees Celsius below freezing. But you know what? It's a dry cold. So Mercury, size-wise, just under 5,000 kilometers, which makes it a bit more than a third the diameter of the Earth. It's smaller than the diameter of Mars. The surface gravity is 0.38, so just over a third of the Earth's. Now, that's actually very close to the surface gravity of Mars, even though Mars is actually a larger planet. And what that basically means is that Mercury is much denser than Mars. And it's almost as dense as the Earth. In fact, if it wasn't for the effect of Earth's gravity, the material that makes up the Earth would be less dense than that of Mercury. So Messenger, a little bit about our Mercury visitor there. So this is what the spacecraft looks like. And being so close to the sun, one of the most prominent features of the spacecraft is a sun shield, which you can see at the back, that white curved structure at the back. Solar power is the best kind of power you can get that close to the sun, so you have 2 solar panels providing that for you. And you can see some of the other major components there. Just go to the next slide. The science instruments, there's a whole suite of science instruments on board. It's what's called the Mercury Dual Imaging System, or MDIS, a gamma-ray neutron spectrometer, GRNS, an X-ray spectrometer, an XRS. Every spacecraft has to have a magnetometer, and Mercury is actually quite interesting in that it has quite a substantial magnetic field, not as strong as the Earth's, but it is still there. There's also a laser altimeter, and that's going to be used to measure the topography of the planet. They have a spectrometer that measures the composition of Mercury's atmosphere. Again, Mercury has a very tenuous atmosphere, a very thin atmosphere, but it is there, and there's a spectrometer on board that's going to measure that. Spectrometer for looking at energetic particles and plasma, so basically charged particles. And then there's a radio science experiment, which doesn't seem to be labeled on that diagram, but I'm assuming it's using, it may be using the spacecraft's main transmitters or another antenna somewhere on there. So how does it get there? Well, this is a bit of a sordid tale, but actually Mercury Messenger's voyage began back in August of 2004. And unfortunately, without a laser pointer here, it's a bit, you'll have to sort of follow along with the diagram there, but basically when it launched from the Earth, it was launched into an orbit that has exactly the same period as the Earth, so one Earth year, but had a slightly higher, it's slightly further away from the sun at one end and slightly closer at the other end. And so what happened was exactly 1 year later, the spacecraft met up with the Earth again. And it actually made use of the Earth's gravity to try and break it and try and slow it down and let it drift closer to the sun. So it does a second flyby of Earth in August of 2005. On this new orbit, which brings it closer to the sun, then it does what's called a deep space maneuver. Basically, it fires its own onboard propulsion and slows itself down even further. In October of 2006, so more than a year after the second Earth flyby, we have a flyby of Venus, and we use Venus's gravity to slow it down. Then in about 8 months after that, in this new orbit, it comes by Venus again. It uses Venus's gravity to slow it down. And then we do another deep space maneuver. And finally, in January of 2008, so 2 months ago, is when it did its first flyby of Mercury. And so we're now a couple months past that. There's another maneuver planned. And then we have a second flyby of Mercury in October of this year. Then there's another maneuver planned, and we have a third flyby of Mercury in September of next year. Then there's a fifth maneuver planned, and we finally arrive in orbit around Mercury in March of 2011. Whew. It's quite the journey there. And in fact, if you look at the upper left there, so we have 1 Earth flyby, 2 Venus flybys, 3 Mercury flybys, for a total of 6 years and 7 months.
Is that all to save fuel?
I'm just getting to that.
Sorry.
No, that's okay. So why does it take so long to get there? Well, let's take the Sun, and let's take the orbit of the Earth. The Earth is orbiting at 30 kilometers per second. That's basically what's keeping us from being sucked in towards the Sun. Mercury is closer to the Sun, so the strength of gravity there is higher, so it has to orbit faster in order to stay afloat. And it orbits at 48 kilometers per second. Now imagine we had a spacecraft here leaving the Earth. So that spacecraft has the same orbit speed as the Earth does. So in order to get closer to the Sun, it actually has to slow down. So imagine we have a little thruster there, and we fire, and what it does is it puts us into this orbit that takes us closer to the Sun, but it's this oval-shaped orbit. It's an elliptical orbit. Now, what we would often do to get to another planet, if we wanted to go directly there, is we would travel on this new orbit for about halfway, and then we would time it so that the planet was there in its orbit right when the spacecraft reaches that point. And at that point, in order to be captured by the planet, we have to reduce the size of the orbit even more. So we fire again, and that puts us into a position to be captured by the planet's gravity. And that process that you see there is called a Hohmann transfer. And if it's a direct route from one planet to the other, it's the most fuel-efficient way of getting there. Now, why don't we just do that to go to Mercury? Well, if you do the calculations, one of the surprising things is that Mercury is the most difficult or most expensive in terms of fuel of all of the planets in the solar system. And I've included Pluto on there just for old time's sake. But
so even though it's falling towards the Sun?
Even though it's falling towards the Sun, because again, in space, slowing down is just as expensive as speeding up, exactly. We don't have air drag or anything to slow us down naturally, so any speed we have to eliminate from us to be ordered to get captured closer to the Sun. So you can see by those numbers there, the sort of change in velocity that you get, or sorry, that you require to do this kind of transfer is higher for Mercury than for any other body in the solar system, I mean, apart from the Sun. But so if you look in the case of Mariner 10 didn't use a Hohmann transfer. It used a single flyby of Venus. But Mariner did not achieve orbit. It did several flybys of Mercury, but it never actually went into orbit. So the reason that they use these convoluted paths to get to Mercury is that by using the planet's gravity, if you time it so that you fly by a planet, and you can use that gravity to actually change your velocity and slow yourself down or speed yourself up in the case of the missions to the outer planets. So that's it's basically, like you said, it's there for fuel savings. So it sounds a bit illogical, but the most fuel efficient route is to go around several times and pass by a few planets and then finally get there, rather than trying to go this direct route. So getting back to sort of Messenger and kind of looking back at Mariner, on the left what you see is a picture that was taken by Mariner 10, and on the right a picture by Mercury Messenger. Now they're not of the same side of Mercury, but what you're looking at here is the difference we're getting in resolution now with the camera technology we have. compared to that of mid-1970s. Okay, there we go. So if we take a look using the narrow field camera on Mercury Messenger, we get something that looks almost like something you'd see in our sort of observers' pictures here. You'd think that could be a picture by Mike Wirth's of the moon, but it's actually, I mean, there are differences, though, between this and the moon, and I'm not going to say what those differences are because I don't want to steal Simon's thunder, but you might want to take a close look at that image and see if you can tell any differences between that and some of the pictures we've seen from our own members of the moon. And if we look even closer, we start to see a lot of topography, a lot of escarpments. So what's next for Mercury Messenger? Again, we have a second flyby coming up in October of this year. We have a third flyby coming up in September of next year. And we're finally getting into orbit in March of 2011. And again, if you want to, if you wanted to have a look at a lot of the images, that's the name of the website there. It's the Johns Hopkins University of Applied Physics Lab is the organization that put together the Mercury Messenger mission. And then after that, well, the Europeans actually have their own Mercury probe planned. And that probe is called Bepi-Colombo. And that takes its name from this gentleman you see on the lower right, who was, his name is Giuseppe Colombo. He was an Italian physicist, very instrumental in 20th century research into Mercury. He was very involved in the flight path and driving the flight path for the Mariner 10 mission. And so the Europeans have planned this mission, and Bepi is sort of a pet name for Giuseppe. That was apparently what he was always known by. So it's a European mission scheduled for arrival in 2019. It uses a relatively new form of propulsion called ion drive. And what that means is that instead of most spacecraft to date, which use chemical engines, they basically heat gases and expel them at high pressures to get the velocity that you need. Ion drive, you basically take particles that have an electric charge and accelerate them electrically. And it turns out to be a lot more efficient, but the problem is that you have such a low level of thrust that you have to fire these rockets for a lot longer than you would a chemical engine. So you actually end up with, instead of doing a single burn and then putting yourself into a nice new orbit, you end up firing this thing for hours or days or weeks and gradually putting yourself into new orbit. So it was kind of interesting because last summer when I was at the International Space University, one of my fellow students there is a Spanish fellow who was doing a lot of his work at ESA on the planning of the path for Bepi-Colombo. And if you think Mercury Messenger's path was convoluted, you haven't seen anything until you see the path this thing is planned to go on. It's a huge spirally path that will gradually bring it to Mercury, but it promises to do some science in conjunction with Mercury Messenger and some science that's in addition to it. So that's basically it, and I guess I'll hand it over to Simon or hand it over to Chuck. Or
Actually, we have a couple minutes for Q&A if anybody's has a question.
Yep.
Well, I want to ask you, you mentioned that the Bepi-Colombo mission will be doing other science.
Mm-hmm.
Do you know what?
Off the top of my head, no. I mean, there was a presentation that this fellow I knew gave, which described some of it. I mean, sorry? Oh, sorry. The question was, what science would Bepi-Colombo be doing different from Mercury Messenger? I can't tell you off the top of my head because I don't recall what instruments specifically are different. But again, some of the science was meant to be done, assuming that Mercury Messenger was there simultaneously, and some of it was science of its own. But you can probably, Bepi-Colombo, if you do a search for it, like you'll get ESA's website on it, and it'll describe all of the science that they're planning on doing. Yes?
When a spacecraft uses the planet's gravity to speed up or slow down.
Mm-hmm.
Does that energy come from or go to the actual planet's momentum? Its orbit?
Yeah, actually what happens, yes, exactly. What happens is the planet loses a little bit of orbit speed, or in some cases gains a little bit. And I mean, the amount that it gains is so, incredibly minute compared to the...
Because of the small mass of the space.
Exactly. So, I mean, it's the similar thing happens if you have a near-Earth asteroid pass by the Earth. I mean, the Earth is going to lose a little bit of speed or gain a bit of speed depending on the path it uses to come in. But the amount is, I mean, when you have a difference in mass, that's that enormous. The effect on the planet is negligible. Eric?
Yeah, jumping ahead a bit, do you think landing a probe on Mercury eventually is viable?
It's always viable. Whether, sorry? Flyable?
No, viable.
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 Well, flyable or viable, yeah. In principle, and there's no reason why not. It's just the, I mean, it's an added bit of complexity. I mean, if we can land something on Venus, have it last there a few minutes and before it melts. I mean, you can land something on Mercury before it melts or freezes, depending on where you landed on Mercury. But there are no plans that I'm aware of putting an actual lander on Mercury. But in principle, there's nothing to say it can't be done. Yes.
After Messenger settles into orbit, what's its life expectancy?
It's a good question. I don't know off the top of my head, but it would be for at least several years. I mean, again, it's one of its primary goals there is to do a map the entire surface. The Mariner 10 gave us the just under 50%. The Messenger's going to give the 100%. But and again, it's been around for 7 years. It'll been around for 11 years or something like that by the time it's actually. It'll be there for 7 years before it settles into orbit. So it'll be at least a few years. It'll be planned operating there. Yes, sir.
I noticed that I believe that Colombo isn't supposed to get to Mercury until 2019.
That's correct.
Why does it take so long? Is this because of the ion drive that?
Well, that's part of it. It's also because Bepi Colombo hasn't even been built yet. I mean, it's I'm trying to even remember when it's slated for launch. It's one of those missions that's been sort of pushed back and in some cases almost canceled, and then brought back. And so it's the launch date and arrival date are a sort of a moving target. But 2019 is the current baseline. And,
Two more questions, please.
yes.
Is there anybody out there worrying that if you have a spacecraft circling around for 6 years, it has a greater chance of being struck by an asteroid or getting caught by a solar flare?
There's every chance of that. In terms of by an asteroid or by actually the bigger sort of risk are from the smaller kind of the very tiny particles, but that's always a risk. But that's been a risk for whether it's the Voyager probes to the outer solar system or the probes to the inner solar system. Solar storms, I would say, are probably much more of a concern for something like Messenger because it's right there at the sun. But again, and Mercury, even though it does have a magnetic field, I'm not sure that it provides that much protection against it. But certainly nowhere near as much as the Earth does. But spacecraft have been operating outside of the Earth's protective zone for years, decades on end, without any issues. So it is always a risk, but it's a manageable risk. Yeah.
Last question.
I believe there was a gentleman. Yeah.
Just wondering if you do the calculation as to what the speed of the shadow on the surface is of the Earth.
Speed of the
Quite slowly. I mean, you could almost drive a car along the thing and stay just at the end.
Yeah. Okay. So the
150 and 400.
Yeah, so the question was how fast does a shadow move when you're on the equator? Or I guess, Well, you can probably do the math. It's 176 days from sunrise to sunrise. So, and I mean, I don't have a calculator in front of me, but you can probably work out with the diameter of the planet, and I mean how far it would actually be the angular rate it would change. But I couldn't tell you without sitting down and doing the calculation. But you know, you
4 kilometers an hour?
4 kilometers an hour. Yeah. So you could outdrive it. Yeah. You got to walk it. Yes.
Paul Harrison, thank you very much.
All right. Thank you.
Our next speaker, Simon HANMER, is a resident astrogeologist. He's helped me quite a bit with my hobby. And Simon is going to continue with the Messenger project. Please welcome Simon HANMER.
Well, Paul's given us a great overview of the Messenger mission, very nicely illustrating the history, the how, and the why. Now, I know many of you have been browsing the images posted by NASA on the web, so I asked Brian if I could take a few minutes tonight to briefly highlight the geological significance of what it is you're looking at when you look at those images. And I wanted to do that before the topic goes cold on us. Great. So I hit, which button do I pull?
That one up.
There, good. I don't even need to walk away from here. Okay, so let me start with a disclaimer. Almost none of what I'm going to tell you tonight has been described on NASA's website yet, but I'm hoping they're going to. There's text which accompanies these various images, and they're rather superficial, and yet by looking at these images with a geologist's eyes, there are some really exciting things already to be seen. There's one other thing I want to point out to you, and I'll come back to it at the end, and that is, can I just remind you of what MESSENGER stands for? MESSENGER stands for Mercury, Surface, Space, Environment, Geochemistry, and Ranging. And what I want to come back to at the end of the talk is the geochemistry part of it. Okay, next slide, please, Chris. Good. All right, so as Paul's already pointed out, at first glance, depending on where you look on Mercury, the surface of Mercury, seen through Messenger's eyes, is rather similar to the Moon. Next one, please, Chris. But elsewhere, on other parts of the planet, there are clear major differences. And some of these were already spotted by that old Mariner probe, and they're extremely nicely illustrated by the new Messenger images. So in this image, you can see there are two very different kinds of landscapes. And I'm looking at this area here in the north, and then the rest of it here in the south and the center. And in the north, you can see these old impact craters. You can see them here, here, here. They're pretty large. But the important thing is they're separated from each other by an extremely rough-looking surface. This thing here looks like a file. And it's characterized by what I'd refer to as heavy pockmarking. And in contrast, the central and the southern parts of the image show extensive, shapeless, and that's important, smooth region, which is made of volcanic lava, and it's cut by smaller and fewer impact craters. But you can also see that the lava plains have flooded and drowned these older, larger impact craters here, compared with these other ones here, which are still exposed. So these two features are very different from what you see on Earth's moon, because on the Earth's moon, these pockmarks are actually quite rare. And where you do get extensive lava plains, because you can see them with the naked eye when you look up at the sky at night, you can see with the full moon those dark patches. Those are extensive, smooth lava plains, but they're confined. They're not shapeless. They're confined to the interiors of well-defined, more or less circular, giant impact basins. Next one, please, Chris. So here's a more detailed Messenger image that shows a large crater, and I mean this one here, plus its other smaller ones around, but that's the one I'm referring to. And it's surrounded by this pockmarked terrain. You can see the pockmarked terrain within the area that I'm referring to here. That's all pockmarked. And you notice these radial crater chains. There's a really nice one there. It's a chain of craters. There's another one up there. And there's another one right there. You see how they're radiating away from the center of the crater there. So those crater chains, those were formed by debris ejected from the impact crater. And this tells us, because of their association, spatial association with the pockmarking, that the pockmarks also represent locally derived debris that was tossed up above the impact site and then fell back to the planetary surface very close to the impact crater. Now this is very different to the behavior of impact debris on the Earth's moon. that is ejected so far that it can fly halfway around the moon before it lands. And you've all seen this kind of thing. When you look up at the full moon, for example, you've seen those bright rays that we see extending from the crater Tycho in the moon's southern hemisphere. And you know from just looking at them, even with the naked eye, they practically go halfway around the moon. So why the difference between the moon and Mercury in terms of these cratering mechanics, if you will? It all comes down to gravity. As Paul pointed out, Mercury is about 40% the size of the Earth, but because it has an unusually large nickel-iron core, nickel and iron are extremely dense, its average density is about the same as that of the Earth, all of which adds up to about 40% of the Earth's gravity. But the Moon, at about 25% the size of the Earth, with a very small nickel-iron core, it has less than 25% of the Earth's gravity. So in simple terms, the impact debris doesn't fly as far on Mercury as it does on the Moon. Next one, please, Chris. So this picture here summarizes the essential features of impact features commonly present on Mercury as seen by MESSENGER. And there are three things to note here. One, the first thing is this double ring crater. There's an inside ring, and there's the outer ring of that crater. Now, these double ring craters, they do occur on the Moon, but they're much more common on Mercury, and they're smaller on Mercury than they are on the Moon. And again, this is a function of Mercury's greater gravity. And in a nutshell, the reason these rings in here form really comes down to the way that the material falls back into the hole when the crater formed in the first place and starts coming in from the outer parts of the crater in towards the interior. And that's where that second ring there forms. So you can see that if material's falling back into a hole, gravity will have an influence. Secondly, in the immediate vicinity of the impact crater is that pockmarked area. See all the pockmarks to the right of a line like this, see all the pockmarking. And that, of course, is derived from the impact ejector, as I say, associated with these radial secondary impact crater chains. There's one beautiful one there, there's another one out there, and there are several others coming up. There's one right there. And it just so happens that the third feature of this image is that in contrast to the MESSENGER image I showed you previously, where the lavas were actually drowning old craters, here the impact and pockmarking is clearly younger than the smooth volcanic plains here to the left of the image. You can see that even the radial crater chains are affecting the smooth lava plains. And because the major phase of impact cratering throughout the solar system is associated with the Great Bombardment that ended 3.8 billion, that's billion not million, 3.8 billion years ago, the presence of smooth lavas that drown older craters, but are also heavily impacted by younger ones, as in this image, that tells us that the lavas themselves probably formed at about 3.8 billion years ago as well. And this highlights another difference with Earth's moon, where on the moon, the lavas that filled up the giant impact basins are hundreds of millions of years younger than the end of the Great Bombardment. Next one, please, Chris. Okay, now these two are not MESSENGER images. They were taken by Mariner over 30 years ago. When Mercury cooled soon after its formation, the oversized iron-nickel core in its interior shrank because the temperature was going down, and that forced the surface of the planet to shrink with it. And that led to the formation of what are called contraction ridges. They're hundreds of kilometers long, and they're a feature that's truly unique to in the solar system. You can see them here. There's one of these fractures here. Here's a close-up of it, exactly the same fracture. And the point of this image here is you can see the curvature of the horizon of Mercury, and that shows you just how big that fracture must be. Well, that fracture, as I said, is due to contraction. And if we go to the next slide, this is a MESSENGER image. It's an incredibly detailed MESSENGER image of a section of one of these contraction ridges. And if you look very carefully, you can see how the planetary crust on the right, here's the section of contraction ridge. And the planetary crust on the right here has moved westwards over the crust on the left here. And what it's done is it's partially buried. Look at this crater right there. It's partially buried it. It's no longer circular. Its southeastern corner is actually overlapped by this material moving up and over this material here. So you can literally see how the mercurial crust moved during the planetary contraction with this incredible MESSENGER image. Next one, please, Chris. Now, this is my last MESSENGER image for tonight. And this is one that NASA is making a lot of fuss about. And I'm going to tell you, I'm afraid it's a rather unnecessary fuss. In typical NASA fashion, they call it the spider. And they associate it with the crater that you can see near the center. Now, what they're pointing at here, of course, are these radial fractures here, going out around 360 degrees, I guess rather like the legs of a spider, if you will. But if the impact crater was really associated with these radial cracks, then it might indeed be a unique feature in the solar system, as NASA claims. Next one, please, Chris. But if you look, it's nothing of the kind. The crater itself is clearly off-center with respect to the radiating features, and it's clearly a late feature that formed after the radial fractures. So, okay, let's now look at this through geological eyes. Okay, we'll look at it through my eyes. Now, if you look carefully in the south of the image, look at this fracture feature right there. That's not a little crack. That's actually a fracture with a finite width to it, and you can see that it's actually a narrow rift valley rather like the Ottawa Valley is a rift valley, where the flat floor of the valley floor has actually dropped down with respect to the walls on either side. And if you look carefully, you can now see that this is the case for all of these fractures. Even these narrow ones here, 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 they're the same kind of thing. They're the valley floors which are flat and will drop down with respect to the shoulders on either side. This is a very common feature on Earth. I was taught about this as a student more years ago than I care to remember. These radiating mini rift valleys represent a failed volcano, albeit a big one here on Mercury. There's the scale bar, so this is hundreds of kilometers across. It was going to be a rather large volcano had it formed. The way this forms is that lava, or molten rock, rose as a narrow plume from the planetary interior. We're talking Mercury here, remember. But it did not reach the surface. So it pushed up the planetary surface, which then cracked radially as it bulged and stretched. Now, the lava ran out radially along these cracks, and as it cooled and crystallized to form solid rock, it shrank because the temperature was going down. So as the ejected lava shrank, the roof of rock above the vertical lava sheet dropped down to form these mini rift valleys, the best one of which, of course, you can see right there. Now, the important point here is that this is a very common feature on Earth, and in fact, one of the best examples is known from New Mexico in the southern United States. It's somewhat smaller than this, but not that much. Now, let me just come back to this business of geochemistry. One of the things that we've not heard about from NASA regarding the MESSENGER flyby is anything about the chemistry of the surface of the planet. And this is extremely important because there are a number of theories to explain why it is that such a small planet like Mercury has such a large, dense core relative to its size. And all of them essentially suggest, or at least two of the major ones suggest, that one way or the other, either due to a collision or early in the history of the Sun, because Mercury was in so close, the outer layers of Mercury were blown away. And so the outer layers were stripped off, the core remained, and the remaining non-core material forms the outer part of the planet. Now, when Mariner went by, it too thought it could recognize the geochemistry of Mercury, and it thought it was made of a rock called a northosite, which I won't get into the technical details of, but it's exactly the same as the white stuff on the surface of the moon. In other words, it's exactly what you would expect to see on the outer surface of a rocky planet in its primitive state. So if it is, in fact, an orthosite that forms the outer part of Mercury, then these theories of accounting for the large core, dense core of Mercury by blowing away the outer layers cannot work, because the composition would have to be something different from an orthosite. The interesting thing is that we know that all of the instruments were operating on MESSENGER, but the one thing we haven't heard anything about from NASA is the chemical composition of the surface of Mercury. Now, I'm not the only person that's noticed that. By the way, if you follow things like Astronomy Magazine and their webpage, then one of their columnists has also raised this as well, and is wondering what it is that NASA is hiding from us. Well, let's hope we'll find out in the next month or so, because it's going to be very interesting when we actually get that result. So my take-home message tonight is this. Number one, MESSENGER has sent us back some wonderfully detailed images. Number two, geologically speaking, there's nothing new that the old Mariner probe hadn't already shown us except for the spider. But the new images are extraordinarily detailed. And number three, the hidden side of Mercury does not seem to contain any unexpected surprises. So finally, what I'd recommend to you is have fun looking at these new images from Mercury. We know that the next swing by will be in October, and we'll get a new batch of really high-quality images of our enigmatic neighbor. For those of you that are interested in a more detailed geological analysis of what Messenger's already given us, I'm going to be sending a more extensive set of images and text to our RASC web volunteers for inclusion on the articles page when they have the time to process it. Thank you very much for listening.
So, open the floor to questions, please.
Way in the back.
Way in the back, Rob?
I was kind of disappointed in Messenger's images because I was kind of looking.
Rob, speak up.
I was rather disappointed in some of the images because I was kind of looking forward to the different terrains that we saw on the moon, where the near side has got the Monterey, the back doesn't, and even Mars with one hemisphere is more cratered than the other, and this kind of breaks the trend. I'm rather disappointed.
There's a reason for it. There's a reason for it. There are two reasons, in fact, because I noticed the same thing. The very first image, if you notice the way that the images came out on the web, they came out in drips and drabs. It was 1 or 2 images a day. And the very first images were absolutely remarkable, remarkably sharp. And then as the days wore on, they got a little fuzzy and a little fuzzier. And then they started analyzing the crater impact statistics with little green circles and so on, and you couldn't see anything in the image at all. And I suddenly realized what was going on. It's a flyby. They're not in orbit. And so only at a certain range and certain speed could they get really good images. But one of the most remarkable things is that on Mercury is a rather large impact basin. And it's a multi-ring impact basin, rather like another rather large one on the moon. And Mariner actually took a better picture. It only photographed half of it, but it's a much better picture. In fact, you can't even see this huge multi-ring basin in the Messenger images. And I scratched my head on this one for a while, and then somebody, I don't know, I forget who, stitched 2 of them together, and you could see immediately why. The sun angle. The sun angle for the Mariner images 35 years ago was really low, and so the relief of all the topographic features came out so beautifully. And on this flyby, the sun angle was really high, and you could barely see some of the same craters that Mariner had already seen. So I think that's the reason, Rob. And it's going to be touch and go for the next 2 flybys as to how good the images are. But once that probe settles into a steady orbit around the planet, we're going to see some remarkable images.
I'll just make a note that the large basin to be named later, the spider's right in the middle of it. Is that right?
It is, in fact, approximately in the middle, yeah.
Do you think the impact itself had a factor to do with this volcano?
No, not at all. This impact is clearly late. It overprints, it cuts across the rifts.
No, I mean the basin itself.
That is conceivable. That is conceivable, although it's very, very different in scale.
It is.
This is, compared with the impact basin, this is a small volcano. It's a large volcano compared with volcanoes on Earth.
Right. Thank you very much, Simon. Okay, I'm very pleased to introduce our next couple of guests, Robert Alexander and Penelope. I don't want to mispronounce it. Goranson? Yeah. Goranson. They're going to, well, give us a surprise. Please welcome Rob and Penelope.
Thank you.
Yeah, I knew it. So please welcome our resident museum specialist, actually, Paul KLAUNINGER.
Hi there, everybody. Well, that's going to be a hard act to follow. Thanks, Penelope. That was wonderful. I'm going to seem very boring in comparison. Can you, oh, perfect. There we go. Don't make that in my face. Okay, Comet Holmes. Well, it's been a year now since Comet McNaught graced our heavens, and I know that a lot of us here in the Northern Hemisphere felt somewhat ripped off by the fact that we didn't really get a good look at the brightest comet in over 40 years. Here in our area, we had exactly one clear night to view it, and only a couple of other nights where we could glimpse it through some stubborn clouds. And of course, we couldn't see it at all when it grew to truly magnificent proportions. Only those folks in the Southern Hemisphere could see that. Well, maybe Mother Nature has a sense of fair play after all, because in October, she rewarded us with what is undoubtedly one of the most unique comets of all times, Comet Holmes. Though perhaps not as spectacular as Comet McNaught to some, it is truly a rare object that put on a show quite unlike any other comet that we've seen. And it was ideally placed for us Northerners. Since its outburst, it has sailed through the evening skies, passing virtually through the zenith night after night. And for the best part of its apparition, the first 6 or 7 weeks after the initial eruption, the weather here was pretty cooperative, giving us a fair number of clear nights and not too terribly cold nights, which is quite a contrast to what we've had lately. So what exactly is Comet Holmes, and why did it suddenly explode onto the scene? Next one, please. Well, Comet Holmes was first observed 115 years ago, and what I'd like to do is read you a passage from the February issue of Sky and Tell. For those that haven't read this, this is rather interesting. The skies on the evening of November the 6th, 1892 weren't all that good, but still found English amateur astronomer Edwin Holmes out under the stars with his 12.5-inch reflector. It would be an early night for Holmes, but just before closing up, he decided to have one final look at Messier 31, the Andromeda Galaxy. After swinging the scope into position somewhat carelessly, he glanced into his finder scope, saw a fuzzy object, and then moved to the telescope's eyepiece. One look caused Holmes to utter, "What is the matter? There is something strange here," an exclamation that brought his wife from the house to see what had happened. Instead of the sprawling galaxy, the view showed a bright, sharply bounded disk of light about 5 arc-minutes in diameter, surrounding an obviously stellar core. Stepping away from the telescope, Holmes looked up and realized that he could glimpse the comet with his unaided eye. He had just enough time to estimate its position before the clouds moved in. Word of the strange new object spread rapidly. On the 8th of November, at Lick Observatory in California, E.E. Barnard reported that the comet's bright coma, now 5.6 arc-minutes wide, was surrounded by a much larger, fainter envelope, 12 arc-minutes across, with a hint of very faint diffusion spreading off to the south. The next night, he wrote, the comet was easily visible to the naked eye as a small, hazy star, and brighter than the brightest part of the Andromeda Nebula. Barnard took many photographs of the intruder, including the one that you're looking at here. Astronomers worldwide watched in wonder as the comet progressively grew in size and faded. Nevertheless, it could still be glimpsed with the unaided eye through November. During December, Comet Holmes became increasingly more difficult to view, its bright envelope expanding and diffusing away. All that remained was a tiny, faint knot of material surrounded by some vague haze that proved difficult to spot even in 12 to 18-inch telescopes. Astronomers expected it to become unobservable within a few weeks. However, on the night of January the 16th, 1893, Barnard and French astronomer K.A. Cobold were both stunned to find a bright 8th magnitude star occupying what the previous night had been no more than a tiny, vague patch of mist. Comet Holmes had sprung back to life. Fascinated, they watched as the star grew ever brighter as the hours passed. By the end of the night, Cobold could once again see the comet with his unaided eye. Pretty impressive stuff. After that second encounter, the comet faded again, and both from the sky and from the attention of most astronomers, at a magnitude never much brighter than about plus 15 since that 19th century outburst. It didn't really get too many observers excited thereafter. In fact, it wasn't seen at all between the years 1906 and 1964. Next slide, please. So what do we know about this comet? Well, we believe it's a small icy body with a nucleus perhaps just over 3 kilometers across and an orbital period of about 6.9 years. Next one, please. Its orbit carries it from just beyond Mars to out almost as far as Jupiter. Other than that, little is known except that for over a century, this flying mountain of ice and dust moved along obscurely, relatively peacefully in its orbit. However, in October 23rd of last year, all that changed dramatically. Next one, please. In the span of just over a day, its brightness increased almost 1,000,000-fold. No other comet has ever been observed to grow so bright in such a short period of time. So what could possibly have happened out there to cause this? Next one, please. Well, some have speculated that since it orbits out near the asteroid belt, perhaps an impact blasted its surface and spewed a cloud of gas and dust into the surrounding space. Interestingly, we actually ran such a simulation of such an event in July of 2005 when the Deep Impact spacecraft targeted a 370-kilometer impactor probe towards Comet Tempel 1. Next one, please. The impactor slammed into the body at 10 kilometers a second and indeed caused a spray of material that brightened the comet for quite some time. The effect was even observable by amateur astronomers here on Earth and was recorded in these next views by the Hubble Space Telescope. It seems unlikely, though, that an asteroid impact is what happened with Comet Holmes. Its growing halo was very symmetrical and very spherical, unlike the cloud unleashed at Comet Tempel 1. Furthermore, the odds of 2 impacts on Comet Holmes producing such a nice uniform coma are, well, probably astronomical, if you'll pardon the pun. As you'll see shortly, there are other observations that also make the impact scenario somewhat unlikely. So what did happen out there? Next one, please. Well, no one can say for sure, but one probable scenario is as follows. Comet Holmes is likely a big chunk of frozen gases mixed with some dust and other loose rubble. Next one, please. If we could take a cross-sectional view, it would probably appear much the same throughout. And we know that every 7 years, it becomes relatively warmer as it nears the perihelion point in its orbit. Next one, please. Since it's a small body, actually, do we have the pointer there as well? Good, okay. Since it's a small body, it's not too hard to imagine that a good portion of the object experiences this increase in warmth to one degree or another. This increased temperature in turn likely causes some of the icy materials in the crust to sublime, that is, to turn directly from solid to gas. This is what typically gives rise to a comet's coma and tail, and you can see in my little illustration here it's starting to sublime there. Next one, please. With Comet Holmes, there's an additional factor. Relatively near passes to Jupiter in the year 1968 and again just recently in 2004 had the effect of decreasing the comet's perihelion distance. Obviously, this would cause the comet to become even warmer during the innermost portions of its orbit. Next one, please. That additional warmth would likely increase the rate of ice sublimation in the crust, leaving it more dusty than icy, and perhaps sealing off the deeper regions. It's conceivable that if the warmth penetrated deeply enough into below the crust, the ices could turn into gas far under the surface as well, as you can see in the greenish areas in this cutaway. Next one, please. If such activity persisted perhaps through numerous orbits, it is possible that pockets or even large cavities or caverns of gas might have formed under the surface. And as more ice sublimed, the gas pressure increased steadily. Next one, please. You can see here, I tried to depict, again, this is a cross-sectional view. You can see that as this is a small body, what I think may have happened here is that throughout areas underneath the crust, we may have had this concentration of pressurized gas forming over numerous orbits. Next one, please. At some point in time, the pressure of this underlying gas at some point on the comet would have exceeded the bearing strength, or the strength of the crust overlying it, and it would have burst forth in a geyser-like fashion. Probably blew a good-sized number of chunks out of the crust out into space as well. And this was no gentle event. I mean, we've measured the gas coma that's been expelled from the nucleus here to be accelerating, or to be speeding out from the coma, or from the nucleus rather, at about 1,300 kilometers an hour. So this wasn't a soft, gentle event. This was definitely an explosive event. The gas underneath that crust must have been at some considerable pressure, if indeed this is the mechanism. Next one, please. And since this is a relatively small body, just a few kilometers across, I think that the shock waves generated by such an eruption would have probably been felt throughout the body, at least to one degree or another. Next. Those propagating shock waves, in turn, from the original eruption, in turn may have been sufficient to trigger yet other eruptions adjacent to it and on further regions of the core. Those subsequent eruptions, again, would generate shock waves, which would, again, propagate throughout the core, or throughout the crust, rather. I've only shown a few jets here, but I could certainly picture a scenario where there may have been dozens or even hundreds of jets spewing material forth in this fashion. That could also explain why the halo was so spherical and uniform, because a lot of the crustal surface was involved in this event. So material was basically being ejected out in all directions. Next one, please. A similar hypothesis to this has been suggested for Mars to account for some of the seasonal dark spots that we see there, as well as for some of the blemishes in thawing polar sand dunes, as this image depicts. Next one, please. While no one can be certain this is what has happened on Comet Holmes, it is one likely explanation. It does, however, beg the question, why don't we see this more often in other comets? What makes Comet Holmes different in this regard? It may be some time before we have a suitable answer to that particular question. So what I'd like to do is just share with you some of the images I've obtained over the last 4 months of this unique event, as well as a few selected images by other observers. Next one, please. This is my first wide-angle shot of the comet as it appeared about 47 hours after its explosive outburst. A good friend of mine, Bob Lavoie, who couldn't make it tonight because of the inclement weather, called me on the night of October the 24th and told me to drop what I was doing and go out and have a look at the sky up at the constellation Perseus. He had just read on the internet about a comet that had suddenly appeared there. I was amazed when I saw this bright new star. It was very easily visible. The moon was up. There was no problem seeing this at all. And this image was just taken with a Canon Digital Rebel and a 70mm lens on a tripod, so nothing special here at all. Next one, please. After seeing this star, I changed to a 600mm lens and was floored to see that this was no star. Indeed, it looked like a small, very bright planetary nebula just over an arc-minute in diameter. Just for comparative purposes, the next slide shows the moon at the same scale. So this is what we were looking at about 2 days after the initial eruption. Next one, please. I've enlarged that 600mm image here by a factor of 10 just to show detail, and you can see that it definitely appeared as a nearly spherical body with no particular sign of a tail or anything else at this point in time. After downloading an ephemeris for the comet and finding its distance from us, I calculated that already at this point it was over 90,000 kilometers in diameter, or about 1/4 of the distance from the Earth to the Moon. That's in a span of just 47 hours or so. This next one, please. This composite, again, all shown at the same scale, shows its rapid growth over the next few nights. After only 126 hours from the initial explosion, it was already as large as the distance between the Earth and the Moon. Pretty impressive stuff. It changed from night to night. This fascinating object. Next one, please. This particular composite, I just used one single image I took on October the 26th, but processed it to various degrees just to bring out different levels of detail. You can see on the leftmost side, this is about as much detail as you got from the inner region. By pushing the processing and bringing out the fainter details, of course, you blow away the details in the center, but you can see that there was a definite fainter outer spherical coma composed of ionized gases that surrounded it. Next one, please. Imaging through a telescope, getting away just from telephoto lenses, but going through a telescope at prime focus, in this case a 6-inch f5 Newtonian, started to reveal structure in the body. The coma had a shell-like appearance and a very bright jet-like core, with obvious elongation there. Oop, my laser's dying a slow death. There we go. An obvious elongation there. Next one, please. And by varying the exposure length, you could pick up the either details in the central region there, or the fainter green ionized gas of the outer coma. Next one, please. During the following nights, the coma and inner jet-like core just continued to grow in size. One of the rather neat things about this comet was the stars that you could actually see through the coma from night to night. It was passing through a particularly rich area of the sky in terms of stars, and you could see those stars as the comet moved. You could see the stars appeared to be moving through the coma itself, and it made observing its physical change in space rather easy to do. Next one, please. By November the 3rd, 11 days after the eruption, the comet had grown to about half the size of the moon as seen from here on Earth. And by taking its true distance into account, its real size had swollen to almost 3 quarters the diameter of the sun. Next one, please. This high-resolution image, taken 16 days after the eruption, shows fine details of gas and dust still emanating from the core, undoubtedly helping to spawn the faint and short tail that was briefly visible, such as in the next image by Jack Newton, taken on the same night. This was a very fleeting detail there. The tail was not visible for very long. And compare this image with the next one taken by E.E. Barnard in 1892. There you can, again, this is just a negative of this particular image, and you can see that the tail has a kink in it, and it looks like it's undergoing a disconnection event. Next slide, please. Does that look familiar? This is by Thorsten Birkel, and again, this was the night after Jack Newton's image, and it shows indeed the tail undergoing disconnection. Rather interesting. Next one, please. Over the next few weeks, the comet continued to grow in size, becoming easily visible to just about anybody looking up at the right part of the evening sky. I think it appeared very similar, though perhaps bigger and brighter than it was first observed in that initial outburst 115 years ago. Next one, please. And have a look at this one and the next one. There's another image by Barnard. Does that look familiar? I find this really interesting that this 3-kilometer diameter object could undergo 2 events, whatever the cause of it, and spawn such a similar looking event both times. Rather neat. Next one, please. By the middle of November, the comet had swollen to a diameter already physically larger than the sun, and it just kept on going. One of the other things I really liked about this comet was that it was visible for over so many nights, and we had a lot of clear nights back then, that I had a lot of opportunities to experiment with different camera lens and telescope combinations, sometimes just doing things very casually and just for fun. You can just flip through a couple of the next ones there. Nice wide-angle view. Next one there. That one was a lot of fun. This one's been all over the internet. I recently found copies of this on some forum that talks about alien invasions. It's wonderful. The internet is just wonderful. Okay.
You're traveling on comets.
Yeah, well, apparently somebody identified those little, if you can go back one there, Chuck, yeah, those Delta Wing spacecraft, they are apparently Kuiper Belt spacecraft, according to the website. I'm not sure.
Not an aberration of your lens, then.
Oh, no, definitely not. No. They were there. I saw them. Great. All right. Some of my favorite shots came in actually the first 2 weeks of December. I think from in our part of the world, certainly the last week of November and the first couple of weeks in December probably provided the best views of this. Next one there, Chuck. You can just flip through a couple of those. You can see how it's gradually growing. Here's one now. It's actually from last month's Astronauts there. Again, you can just flip through there. Yes, definitely. And I think my favorite, I think, is the next one there. Yeah, that one, I particularly like this one. At this point, the comet was nearly twice as large as the full moon in the sky, and from our point of view here on Earth. And in real times, it had already grown to 3.5 times the diameter of the sun. Now, how does a little ball of gas and dust and ice 3 kilometers across spawn off enough material to grow to 3.5 times the diameter of the sun? If you do the math on it, that's like 30 times the volume of the sun, and we can still see that. I find that's pretty impressive, and maybe it is alien spacecraft, I don't know. That website, by the way, they were saying that one other speculation was that those were actually Earthen spacecraft, and we were going out to target and destroy the comet. I didn't write that. Anyway, the night of the Geminid meteor peak, I was also fortunate enough. I was doing some imaging, and I managed to bag a Geminid in the same field as the comet. That was a lucky shot. Fun though. But afterwards, after that point in time, after the middle of December, the weather certainly turned here. As we all know, we're approaching a record season for snowfall here, and we certainly had a lot of cloudy and snowy nights since the middle of December. But at that point in time, the comet was already starting to fade. It kept expanding, but it's also moving farther away from us. We were really lucky with this initial apparition there, because at the time that it exploded, it was pretty much as close to us as it was going to get, about just over 1.6 astronomical units away from us. It's now about 3 astronomical units away from us, so almost twice as far away. Still visible in the sky, but it's definitely diminishing because of the distance and because of the fact that the coma is in fact still expanding. Next one. Here, I did manage to get a couple of clear nights in there as the new year broke there. And next one again, but you can see it definitely fading. These were all taken with the same equipment, essentially my Canon Digital Rebel 300mm telephoto, piggybacking on a telescope for the various lengths of times that are shown down below there. January 25th, next one there, you can see it's really starting to fade away. February the 1st, and I think I've got February the 12th. Again, just really. Starting to get almost lost in the sky background. And I think I've got one more there. Yeah, that one I shot just a week ago, and there it is there. Yeah. Now, mind you, that was, if I'd shot it earlier in the evening, it would have been brighter there. This was already at only about 12 degrees elevation there. So obviously I got some attenuation there, but yeah, definitely getting faint. We had a bit of a clear spell last night, and I did have the binoculars out under a fairly dark sky, and I could see no signs of it with the binoculars. So I have one thing left to show you, and Chris, if you want to change over, Chris is just going to change over there. Oh yeah, I'll have to show you this slide. What I did is, because we had so many nice clear nights, I took one of the things I did on purpose was to take whatever other configuration I was experimenting with. I took a picture of the comet with the Rebel and the 300mm lens consistently on different sessions there, so I would have essentially a collection of images all taken at the same scale. I've stitched those together into a short movie sequence just to show you how the comet has expanded over the last 4 months. And this slide is for reference. For the images that you're about to see, this would be the moon taken with the same camera configuration, so at the same scale. So Chris, whenever you're ready, you can let that roll. Media player's working on that one. I didn't build in this very pregnant pause. Just in closing, just have to wonder when we might see Comet Home's next rebirth. Thank you.
Okay, our next series is, I guess Tim's not here, is he?
I haven't seen Tim, our next speaker. So you may have the challenge, Chuck, of explaining Tim's slides on
Uh-oh.
on the fly.
Well, I haven't even seen them, so what we'll do, we'll let the slides go and see what happens. If anybody wants to go in, I guess,
We may need the lights down.
yep. I'll just get them down.
Yeah, there, it's done. It's fine, Chuck.
So I really haven't been briefed on this, so we'll just let the slides go, and if anybody has anything to say, I guess we can say it. I'll tell you, that night was fantabulous, wasn't it?
Great seeing that.
It was. I think it was the first one my daughter saw. 9 years old. Okay, here we go. Almost springtime, eh? We're Canadians, no problem.
Maybe we switched to daylight saving time this weekend.
This weekend too, is it? Spring ahead. Don't forget, tomorrow night. Thanks for the reminder.
That's a nice shot.
Okay, this one here, Brian wants to make this announcement. What's it called? Okay, Earth Hour. Was it Sydney, Australia?
I can give some background for the people who don't know it. This was an event that happened 1 year ago, started in Sydney, Australia, where the city of Sydney asked everyone to shut off their lights for 1 hour. And basically the entire city did it. Since that happened a year ago, they have expanded the program, and it happens on its anniversary this year, March 29th. And there's a long list of cities around the world that have subscribed to it. And one of the nicest surprises is in Canada, Ottawa, just about a week ago, Ottawa City Council enacted a bylaw supporting Earth Hour, along with Montreal, Toronto, and Vancouver, and are asking everyone on Saturday, March 29th for 1 hour to turn off all lights and celebrate dark skies. Great to see Ottawa joining in.
Yeah. Let's
Include the TV?
let's just hope it doesn't snow.
Some of those people have never seen Star Wars, right?
Yeah. Well, during the last power failure, I sat out in the backyard, and my score was, I think, 5 meteors and 3 satellites, and a glass of scotch.
More satellites.
Yeah. We won't get into that one. Okay, I guess we'll get into our observations.
We start, I believe, with Rob Dick.
Okay, Rob, come on up here and rock and roll from there. Where are you? Can you see where you're going? There he comes.
I was planning to take some really nice pictures through my 12.5-inch telescope of the lunar eclipse, and then I got a call from the museum to come in because they're going to have a flood of people. So I had the pleasure of, instead of having a 12.5-inch equatorially driven telescope, I had one of these little tripod-mounted 3-inch stubby refractors for the public to look through. And so unfortunately, I couldn't put a camera there because the eyepiece was there, so the public's supposed to look through it. So I had the pleasure of having a rickety little tripod with a not so good telephoto lens on it that I had to crank down. As you probably imagine, it's kind of low, and you're kneeling in the cold muck and so on, and trying to take a good picture. That limits your exposures to very, very short because there's no drive. So that wasn't too bad for the first part of the eclipse, but during totality, you need much longer exposures to pick things up, and that's where it gets kind of blurry. So this is kind of a memory. So some people wanted some pictures. Some of the public came by and they wanted to get my pictures. They saw I was taking pictures, so I've sent this off to a number of people. I'm a little sad that it's not very well focused, and that's because of the rickety little telephoto lens. Canon makes a great digital Rebel camera, but their lenses are pretty poor. Let that be known to everyone. But it was a nice memento, and perhaps the biggest memory that comes up with this is that we had over 300 to 400 people here at the museum lined up at the telescopes, and they lasted for 2 hours. And we lasted for 3 hours, but we didn't feel after about 2 hours, you don't feel your feet anyway. And that's about the exposure is about 300 millimeter telephoto lens on the Canon Rebel, and exposures range from a fraction of a second to about 2 seconds or so. Okay, that's it.
And on that note, I sincerely want to thank all the RASC volunteers that showed up for this event. It was very, very successful. We have a letter of thank you from Mr. Lebrec from the museum. Just bear with me, I'm going to read it here. Many thanks to all RASC volunteers for lending a helping hand in last night's eclipse program. It would not have been the success it was without the strong show of support. The weather cooperated, enthusiasm ran high, and the visitor turnout was totally amazing. I did not expect 200 plus people to show up. And Garab and everybody, thank you so much. Thanks again to all who helped out and braved the minus 20 degrees Celsius temperatures. The next astronomical event in our horizon is the International Astronomy Day 2008 on Saturday, May 10th, hopefully under clear but warmer skies. Thank you, merci, Michel Lebrec. Perfect, and thank you again from me. That was great. Okay, who's next? Bob, where are you? Bob is always showing great stuff.
I took some pictures of the moon during the eclipse, and this is my total eclipse picture. And this is a 1.5 second exposure. It's an RGB, and as you can see, it's just this gorgeous red. We didn't see it quite this bright because the camera sees a little better than we do. And Attila described this as the sunsets and sunrises around the entire Earth. And I thought that was a really neat description, exactly what we saw. Okay, next one. I made a little animation of the eclipse. And this is through a red filter and 1,000th of a second, which is as fast as my camera will go. And I could not take a 2/1,000th picture, otherwise it was overexposed. So this picture now is basically 1,500 times less exposure than shows on the last picture that you just saw. So when the moon is totaled, it's totaled now. You won't see it. Okay, can you run it? Okay. This is the shadow. I outlined the shadow. And there's the center heading over top of the moon. Now you'll notice that it's not going horizontal to the ground. That's because my camera had a slight angle to it. you have it without? Now this is it without the shadow outlined. This is my first animation. It only took me maybe 40 hours. Had to learn the software. I did this, by the way, in Doug George's Maxim. It's the only thing that I had that would make animations. You'll notice that you cannot see the moon at this exposure. One of the interesting things about this is the moon really did blank out, and you could see all the stars all around it when it was blanked. It was, like I say, 1,500 times dimmer than full moon. Okay. This was the astronomy challenge for the last month, I think. Or no, the month before. I was away. And this is an interesting star field that, and I looked it up on the net, and it said, oh, it's 1.5 billion years old. And I thought, oh man, I'm looking at something like 1.5 billion years old. And then I suddenly realized our sun is like 5 billion years old. So it wasn't so spectacular. But these stars right here, the orange ones, are giants, and in that 1.5 billion years, they've turned into super giant reds. So this is a star cluster, all created about the same time, but some of it's dying now. Okay. This is the challenge object, I think, last month, the horse head. A couple of things I'd like to show you about it. First is Alnitak right here, which is one of the 3 stars of the belt, Orion's belt. It's 11,000 times brighter than our sun. That's if you don't include the ultraviolet, because it's so hot that it's producing a lot of ultraviolet. If you include the ultraviolet, it's 100,000 times brighter than our sun. And it's only a few million years old. So it's pretty young, and will burn out. It will turn into a red giant eventually, shortly in sort of astronomical terms, and probably supernova. It's a good bet. The red back here is all hydrogen that's been excited by the very, very hot stars around it. It makes a wonderful curtain. The Horsehead Nebula, of course, is right here. My fiancé said it looked like a goat. The Flame Nebula is lit up by a star that's right in behind that little tongue of black. It's again, and the blue that you see right here and down here, and I guess these ones also, they are just stars that are being formed out of dust, and the dust is collapsing. And what you're seeing, the blue, is the light that's reflected off the dust. It's sort of like what makes our sky blue. Same kind of idea. And I should just make a comment about the developing of this, or the processing of this image. When I process an image, I have a red, a green, and a blue image, and I combine them to make a color image. No problem. Make the black black, make the white white, and you're off the hook. Except now I've got red and I've got blue that everybody knows about, and they better be red and blue. And so this becomes a lot tougher than just the ordinary kind of image. Okay, next one. And this picture I took with my longer focal length telescope, just of the Horsehead itself. It's a much higher resolution image. I think that's it.
Great, thank you very much.
Thank you.
Fascinating as always. Is Rolf's up next?
Nope.
Oh, Chris. Oh, Chris.
Very quick description. A long time ago, I booked something very rare for me, a southern holiday, and little did I know I picked Eclipse Week. And I was privately laughing that here in Ottawa, you probably had a little chance of seeing it with clear skies, and I had great chances in the Bahamas. Ended up being the opposite, as you can see here. I fought the whole evening with clouds. But managed to get that shot between some of the clouds. Yeah, I was in incredibly dark skies with the next view to in this direction after where I was Africa. So it should have been great conditions and was lousy. So, but I had to at least prove I was in the Bahamas. All I had was a camera and a tripod that fitted in my pocket. Rolf was going to give an entire talk tonight, or in fact a 2-part talk on Mars, and he's decided not to come, living as far out as almost Almont, and not wanting to brave the weather, but he did send a few of his shots of the eclipse. This one, the overall view taken from inside his observatory. hopefully he'll give his talk next month on Mars. I don't know if Murray is here tonight.
All right, come on up, Murray.
You'll find this interesting. This is my continuing saga of my cat's black. This is the Rasc challenge for the lunar. I took a couple items with it and I forwarded to Brian. What we see here is an overview showing the edge of the terminus, and for the little hole there for the tubbit. This is an enlargement of it. What I found about this was that it was shaped as a squash bean. It did not look like the there it is. Did not look like the Kool-Aid Man as was advertised a few months ago. But what I was amazed by it was, in that particular view on that day at that time, I was able to see the terracing that was happening in it, and it had at least 3 layers going, so it had some cave-in effects for a sub what's the term? Sublimation or whatever it is? Yep, subside. Whatever you do it. Yeah, and I think I have another one after that. Yeah, same thing. On this one, it had a different type of view, same type of affair. It was white, really bright. It showed lots of contrast there, so you saw some other effects. So that's it. I tried during the eclipse. I tried looking at this as gain. It looked really great during the penumbra. But when it was all oranged over, everything, all the features faded to black almost. I have it. Contrast here. Okay, that's it.
Thank you very much. Murray, with the word you're looking for, was it slumping, crater slumping?
Oh, caving in from the sides?
Yeah, that's right, yeah. Basically, after the impact, the walls are unstable and it just poof, slumps down.
Oh, I got the sequence wrong. I don't know if Gary is here tonight. I haven't seen him.
I don't think Gary is, no, I didn't see him. So we'll just let it go through, I guess. So this is the picture of, that's about it, I think.
Tebbit, I believe, is right there.
All right, okay.
Those are all in focus.
Always fascinating to see.
Go that one. That's worth having a close look at. Look at the valley right down the middle of the Rift Valley.
Oops.
That's it, right down the middle.
Yeah, right down in there, yeah. So there's a rill right in the valley, basically.
Exactly, that's the collapsed lava tube.
Uh-huh. And is that a rift valley itself? Yes. Rift and then a collapsed tube inside it.
The classic Rift Valley on the moon.
Okay, and the that word, that's means
Chain of craters.
chains of craters, yes. I won't even try to pronounce it. Katina. And this is the observer challenge for this month, courtesy of Brian. So make a note of that. That's Brian expects some results from this, I guess. New March Lunar Challenge. There we go. Catching up here.
Davey.
M41, okay.
And this is where you have the text.
Okay, my cue, sorry. Yes, please. Thanks, Stefan. Do you need the pointer?
Oh, that's okay.
Yep, okay.
This is my first time up here. I've been a member for a few years, but I don't get out as often as I like to, and I'm usually just hiding up the back. But I had a few pictures that I got some positive feedback on. This past summer, I was in Hawaii, and I got a chance to go up to the summit of Mauna Kea. And there's beaches and things in Hawaii, but really, if there was nothing else there, this would be worth a trip in itself. This is sunset on Mauna Kea, and I just had a little point-and-shoot camera, and I was able to stitch together a really wide panorama of about half a dozen shots. And if you want to do panoramas, it's actually fairly straightforward. You just set your camera to the landscape mode where the focus is set to infinity. and you set the white balance to a manual white balance setting so it doesn't change partway through. And to keep the exposures consistent, if you have a manual camera, you can set the aperture and shutter manually, or if just a point and shoot digital camera, you point to a part of the sky that gives you the right settings. You push the shutter halfway down and it locks those settings in, and then you point to where you actually want to take the picture and push the shutter down the rest of the way. So that's how I was able to take 6 pictures with a point and shoot camera that I was able to stitch together. So there's the view from Mauna Kea.
Nice big cumulative numbers there.
Yeah, it was raining really hard down on the coast that day. So this next one here, I work for a company that does airborne geophysics, and we were doing a survey along the shores of the Mackenzie River a couple of years ago, and it was really cold, but there's such a strong current on the Mackenzie River that there'd be a little bit of steam just off to the left there that was turning into ice crystals, and those are floating in front of the sun, and that was causing a really bright pair of sundogs. That's sunlight that's refracting off of the ice crystals. And so on either side of the actual sun, which is blocked by the helicopter rotor, you can see there's 2 kind of fault suns. And then, that previous image was in the Sky News magazine in the Reader's Gallery, if you saw in the January-February issue. So it was, yeah.
Well done, well done.
And the last one here, the previous year when we'd been doing the survey, there was great northern lights, but the point-and-shoot digital camera just couldn't capture them, so I brought my old manual film SLR camera, and the following year there was great northern lights again, and I was able to capture this picture. It's a Kodak, Fuji Chrome Provia 400F film, and I didn't bring a tripod with me, so I just wedged the camera in a snowbank and wedged myself in the snowbank, and I think that's a great thing for those old manual cameras because the battery won't die when it's -30, and you don't have to worry about snow and ice gumming up the electronics because there aren't any. And this image has actually got some positive feedback. It ended up on the cover of an obscure mining journal this month, so that's it.
Perfect.
Nice shot of Ursa Major, too.
Yeah. How far north did you get, Stefan?
That was Leah on the Mackenzie River.
Okay. Did you get up to Tuktoyaktuk?
No,
Yeah. Okay, this was the January challenge, and this is the image of course, the horse head, and I want to introduce our next speaker with this is Rick Wagner, and he's going to give us some entertainment on this, I hear. Please welcome Rick Wagner.
Yeah, so it was the challenge object for January. Laser pointer, okay.
Did you find it?
There we go. Now, unfortunately, I didn't know Bob Olson was going to come up with his image, so it's a little embarrassing comparison. I have a little longer, shorter focal length, so I'm getting a wider field of view than Bob is. So you can see it's actually a really interesting area. Even though the horse head itself is very difficult to see and requires very good skies, there's a number of other things in the area there. There's the horse head, of course. Alnitak is the bright star Bob mentioned. And then there's a number of, in fact, this whole area, no doubt you've heard Glenn talk about the OB Association in Orion, and basically the whole area is just jammed with very young, bright blue stars. And so with the core, the dust around them, so these are IC 431, 432, this is NGC 2023, and this is IC 435. The red glow against which the, oh, there we go. Oh.
I was waiting for you to ask for that slide.
Okay. The horse head is actually silhouetted against IC 434. This nebula here is quite bright. It's the Flame Nebula NGC 2024. It's easily visible in a scope. It's good to keep the Alnitak out of the field of view to see it. 2023 is also pretty easy in a scope. The remainder of these little guys, though, I have not seen. They're quite difficult because you've got a very bright blue star with some very faint blue nebulosity around it, so that it's very easy to lose the nebulosity and glare in the telescope. This guy right here is really interesting. This is Sigma Orionis, and it's actually the brightest star in the Sigma Orionis cluster, part of the OB1 association. And what's really neat about it is it's actually a multiple star. I can't even remember it offhand, but there's several components that are visible in a telescope. Plus, then most of the components are also spectroscopic binaries as well. So there's actually about 6 or 8 stars all orbiting around each other. And the other interesting thing is the cluster itself. About 6 weeks ago, I read a paper on basically practical astrophysics. You can examine the colors of the stars, or even ideally the spectra of the stars, and you can determine their color, their temperature, the gravity, and essentially what it works out to is you can get their distance, their actual magnitude. And this paper just goes through about 19 stars in the field of view and does a detailed analysis of each star to try and fit it all in a Hertzsprung-Russell diagram, which you can then use to determine a very accurate distance to the cluster. And I'm going into major nerd mode here because I just found this paper was just absolutely exciting, because every star, there's several pages of analysis on the details, what you have to deal with. There's reddening issues, and how to convert the photometry into temperatures, and on and on. You could base a whole year of university course in astronomy on that one paper. I think that's... Oh, well, the interesting thing about this, of course, is this relates back to Paul's talk, is this is Barnard 33. It's a dark nebula. One of the things E.E. Barnard did was he did a bunch of photography. He actually had a special 10-inch camera lens designed to do photography of the sky, and he cataloged, I can't remember the total number now, but in the range of a couple of hundred dark nebulae around the sky. And at the time, there was a big debate around the world about, are these actually just holes in the galaxy where we're seeing out into empty space, or are they actually dark clouds intervening? And it's interesting, Barnard didn't seem to be entirely convinced that they weren't holes, but very shortly after Barnard did his catalog and stuff, it was pretty well settled that they are in fact dark nebulae. And to look at them nowadays, it seems very easy to see that, well, clearly this little dark cloud is in front of, and dark in front of a bright background. So if we go to the next slide. So this one isn't my image. This is the NOAO, one of the big observatories. And the reason I've wanted to do this little talk for a number of years now, and it gives me a chance to embarrass Rob Dick. So Rob came up in January and definitely showed a little, I think, confusion over the Horsehead Nebula. Well, it's the horse's head. So if we go to the next star, our next picture, you can actually overlay the head of a horse, but it doesn't fit all that well. I tried a couple of other chess pieces and they didn't fit any better. So next slide. I guess I can do that, eh? Okay, so we put a real horse head on, and it's looking better, but it's still not great. So if we go to the next, you notice this line of wisp of nebulosity down there. I don't know if Barnard even would have seen this, but it definitely looks like a tail. And so we can sort of begin to see that maybe Rob Dick is vindicated, that this isn't really the Horsehead Nebula. I think we've got a perfect fit. And clearly, we're looking at the wrong end of the horse. So, in my less politically correct moments, I'm proposing that we now call this the Politician's Nebula. So, I think that's it. Thank you.
Thanks very much. Anyway, thank you very much for coming, everybody, and we'll see you next month.